Hi, everyone. So we are going to go ahead and get started. My name is Carrie Ann Wilson. I just finished my first year of my PhD at University of Michigan, and I'm starting my second year. So today I will be moderating Dr. Alex Kavner's talk. So Alex recently defended his dissertation and graduated from the University of Michigan with a PhD in applied physics. His, his dissertation research is on decay energy spectroscopy and the utilization of magnetic microcalorimeters for accurate isotopic analysis of nuclear materials, precision half-life measurement of samarium-146 relevant for determining the timescale of early solar system formation, and the potential use as a sevens or dark matter detector. Alex's career ambitions are to develop nuclear safeguards and technologies for strategic initiatives, as well as to design experiments aimed at measuring relic neutrinos. He is currently working at the University of Zurich in Switzerland. Today, he will be giving a talk on dark matter and neutrino detection. So as always, feel free to use the chat question to answer any questions, and I can attempt to address them while Alex is speaking. But this is a little bit out of my wheelhouse. And so if I don't know the question, I'll just wait and we'll talk about it at the end of his talk. All right, Alex, so you can go ahead and take it away.
All right. Thank you, Carrie Ann. As she mentioned, I've kind of worked in a lot of different detector physics techniques, and some of that has been dark matter and neutrino physics. And my current research ongoing now is also going to be in neutrino physics, or dark matter and neutrino physics, which are fairly related, as I'll hopefully show in this presentation. And then additionally, I hope that I'll convince you of the interest in physics in this and why it's actually fairly relevant, at least from a skill set perspective, to nuclear engineering and also the other topics that have been discussed so far in this summer school. So this really turned out to be more of a neutrino talk than a dark matter talk. Carrie Ann, can they see the full presentation mode and not my notes, correct?
No,
Oh,
we see it like looks like when you're editing it in
okay.
PowerPoint
There.
is how it looks. All right, there you go. That's
All
good.
right, perfect. Well, not very technology inept. All right. So this turned out to be more of a neutrino talk because we've actually detected neutrinos, and I wanted to talk about experiments that actually detected things. And then I'll tie that into how dark matter detection techniques work. I'm going to try and keep this to about 45 to 50 minutes. And then we'll have some time to answer questions at the end. I'm going to go over what are neutrinos, the neutrino discovery, something called the solar neutrino problem, then some modern neutrino experiments, and some modern dark matter experiments. So hopefully you've seen something that looks like this in the past, if not in this course. And this is the standard model of particle physics. And it's really the periodic table of the fundamental particles as we know them today. It's broken up into 3 to 4 sectors, depending on how you call it. There's the quark sector, which is up here in lavender, the lepton sector here in green, and then the boson sector, which is here on the right, where there's the fundamental force bosons in the orange, and the Higgs boson, which is a bit different, and that's a bit beyond the topics of this course. But you can think of the 3 most important particles, first being the up and down quark, and these are important because they make up the proton and the neutron. And then if you expand it 1 row down, you include the electron. So then, the constituents of the proton and the neutron plus the electron, and that really makes the atom. So then 99.9% of things that you interact with in your daily life involve those 3 particles. However, there's also the muon down here, which you actually also interact with a fair number of those from cosmic radiation. And then down at the bottom, there are the neutrinos. Sorry, it's which pass through you with very rare interaction. And the necessity of the neutrinos from a theoretical standpoint really comes from just there needs to be a symmetry in the periodic table, a mathematical symmetry. So because there's these three generations and two kind of helicities of quarks, there also needs to be these charged leptons and these uncharged leptons. And that presents itself in fundamental physics in that the number of these fundamental leptons or quarks in any sort of reaction need to be conserved. And we'll talk about that a little bit more. And then going beyond what's shown here, there's other hypothesized particles such as dark matter, graviton, which would be the fundamental force particle for gravity, and additional neutrinos that may not be discovered yet, and anything else that people have or haven't even thought of. So the neutrino actually goes back to about the 1920s in terms of its its existence in theoretical physics, which people might think of being a lot longer than what it has commonly been thought of. But the original idea for it came from the observation of the decay of helium-6. So you have a helium-6 nucleus within a cloud chamber that just, the radiation moving through the cloud chamber causes nucleations of bubbles, which show up. And the decay energy of this is really high. It's about 3.5 MeV of excess energy, which means it has a short half-life, about a second. And because it's a very neutron-rich element, it'll decay into lithium-6 and a beta particle. So a proton goes to a neutron plus a beta, or sorry, let's undo that. A neutron goes to a proton plus a beta particle. There we go. This was not yet discovered at the time, so it was just thought that, 6 helium goes to 7 or 6 lithium plus a beta. And from observations of these decays in the cloud chamber, you can see that these particles do not go back to back, which is a big problem in fundamental physics because one of the founding underlying assumptions in all of physics is that momentum is conserved. So if you have this particle at rest and it breaks up into two other particles, which are not going back to back, you seemingly have momentum coming out of nowhere. So Wolfgang Pauli, who is over here, thought that, okay, maybe there is some third particle that is unknown, some third unknown particle, there we go, going out of this reaction. And Niels Bohr, who is another fundamental player or foundational member in physics, said, nope. He thought that momentum conservation, that, the concept that PI is equal to PF was not true at a fundamental physics level and only true at a classical non-quantum mechanical level. And for us sitting here in 2024, that might seem like a really dumb idea, but in the 1920s, 100 years ago, there was some fairly good reason for that. So if you go and were to, let's say, make a graph of, time in years, and then, on the access here, we say the number of theorized fundamental particles. So in 1920, this is not going to be a linear scale. This number was at an all-time low of 2. You had just the proton and just the electron. And if we go back in time, they previously thought that there were, say 100 to 200, which were the periodic elements. Not, they didn't have entirely 200, but it was theorized to be somewhere in that regime. There we go. Some theorized to be somewhere around there. And if you go earlier in time to antiquities, we'll say that there was about 4, which were earth, wind, fire, and air. So from 0 to, we'll call it 1850, the number of fundamental particles went up, and then it started going down when the discovery of protons and electrons. This is really, we'll call it 1900 is when it's going down. And then this is when Pauli is proposing the neutrino, when it went from 150 fundamental particles to 2. And then since we know that it went up again, and then has since gone down, and now might go back up. And this is with all the pions, mesons, hadrons. And then, we were down here when we had the standard model. And then, question as to where it will go after that. Not very nonlinear scale, but I hope what I'm saying, what I'm trying to convey is in the history of particle physics, the number has been highly changing. And at that point in time, they thought it was 2, which everyone was happy about. But as history has shown that it's wrong, that really what is happening is there is a neutron. The neutron was then discovered shortly after in 1932. And when that happened, Enrico Fermi came up with a new theory of beta decay, where you have this neutron that then goes to the proton, the electron, and then agreeing with Pauli's assessment, the neutrino, which is actually denoted as an antineutrino, but we're going to call it a just neutrino for the sake of being. But there is a distinction and also a big question of, are these guys the same as antineutrino? Are neutrinos and antineutrinos the same particles or not? And then from the quark view, what you have going on is you have a neutron, which is an up and 2 down quarks, being transformed into a proton, which is 2 ups, and a single down quark being moderated by the W boson, which was on one of the previous slides. And then this W boson goes into an electron and a antineutrino. And then the reason why this is an antineutrino is because this is a regular particle. And as I mentioned earlier, the number of particles and antiparticles in the lepton sector or the quark sector must be constant. So a lepton and goes to +1, and then an anti-lepton goes to -1. And so we have 0 at the beginning and 0 at the end. And so that's important. So then scientists started thinking, okay, how do I go and try and detect these neutrinos or antineutrinos, whichever they might be? And so the thought was, okay, if a neutron can go to a proton plus an electron plus a neutrino, then maybe I can rearrange these kind of questions. So what happens if I start out with a proton and a neutrino? Then can that go to a neutron and some other kind of particle? And the charge also has to be conserved. So you have a proton is a +1 charged object. A neutrino has no electric charge, so +0. And then on this side, the neutron is a neutral object, so +0. And then, so instead of an electron, you now need to have a positron, so a positively charged anti-electron. And so then this, from a charge standpoint, also becomes +1 charge. So we have, on the left side, +1, and on the right side, also +1. And then from lepton conservation, we have the proton is made of quarks, so that's 0. The antineutrino is -1 leptons. The neutron is 0 again, and the positron is an anti-electron, so that goes to -1. So -1 equals -1, so we are happy. So we're happy that that's conserved. And then the proton is made out of 3 quarks and the neutron is made out of 3 quarks. So that is also conserved. So what does this look like in a more actual experimental kind of candidate? We want to describe this kind of as inverse beta decay, or the other way to think about it is anti-neutrino capture. So you have the neutrino coming in, and this gets captured on the proton, and the proton turns into the neutron, which goes off, and the positron is an antiparticle. So the positron E plus the electron, it'll find some electron, which are everywhere, will annihilate each other, and they will just go to 2 gamma rays. And the energy of the gamma rays is 511 keV, which is the rest mass of the positron and the electron. So they have to conserve energy and also have to conserve momentum. So these 2 gamma rays will be emitted back to back, such that the momentum is conserved. This neutron then, and you guys have talked about neutron detection and measurement a few times, I think, in this course, but it will go around, it will thermalize, so it will bounce around within whatever material this is occurring, and then will capture, oops, that's not there, will capture on hydrogen or some dopant. And the lifetime of that depends on what it's being captured on. If there's nothing but other protons, then it'll be a few hundred microseconds. And then if it's a something like cadmium or gadolinium, it'll be much quicker, which we'll discuss. So what makes a good neutrino detector? You want something that is proton rich, or I should say anti-neutrino detector. You want something that has a lot of protons. So something like water or plastic is a very proton rich material. You want something that has a high neutron capture cross section, which will then detect those emitted neutrons. And that could be something like gadolinium, cadmium, lithium, or boron. And the really nice thing about all of these is that they're cheap. Water is a fairly cheap quantity to make or purify. Plastic is also fairly cheap. And, gadolinium, cadmium, lithium, and boron are also not particularly expensive materials when you say are talking in comparison to other modern detectors like lanthanum bromide or high purity germanium. And so this is kind of what a modern neutrino detector looks like. The plastic that's used now is a plastic scintillating material, which I believe you guys have talked about. And what you'll have is a lot of, protons in the plastic. You'll have plastic that's doped with, your lithium. We'll just say, for example, it's lithium, but it could be any one of these. So you have lots of targets for the neutrino to go and capture to. The neutron is produced and goes and gets captured on the lithium, and the positron goes, annihilates with some electron, and you get those back-to-back gamma rays. And then these are all detected in uh, a detector that's about the size of a person. This is a design concept on a paper published by Felicia Sutato, who is another graduate of the NERS department. I know she's given some of talks on in the MTV series in the past. I'm not sure if she did this year, but she's someone who's very versed in designing these kind of detectors. So now that we have a detector concept, what about a neutrino source? We need something that provides neutrinos. So the most obvious first solution that people thought of is, okay, what about nuclear fission? Um, you get production of a lot of unstable nuclei. So the fission event happens. You get radioactive daughter products, and these guys go out and decay via beta emission, and each beta emission must also become or come with a neutrino. And you also, when you have a lot of fission occurring, you also get a lot of neutron capture on various elements, which can also beta decay and also emit neutrinos. And the other nice thing about fission is these are relatively high energy neutrinos, or both neutrinos and betas, that the beta energy and neutrino energy are, greater than 2 MeV for a lot of these decays of fission products. And that's important because in the neutrino capture equation, proton plus neutrino goes to positron plus neutron. You need about 1.8 MeV in order to get the threshold of this reaction going. So fission is the obvious first choice because you get a lot of you get at on average 6 to 7 neutrinos per fission event. So you get a high neutrino multiplicity, and a great many of them are above this 1.8 MeV threshold. So the first thought was Hans Bethe, who is a nuclear physicist at the time and very famous for a lot of work that he did in nuclear fusion, particularly when it came to stars, as well as his work on the Manhattan Project, did a rough calculation that the cross section was 6 times 10 to the minus 44 centimeters squared, or for example, that is about 20 orders of magnitude less than the cross section of fission. So the probability of a neutrino being captured on a proton is 10 to the 24 lower, 22 lower than a neutron being captured on a proton or on a fissionable nucleus. So his answer was, you will never detect neutrinos with that brutal math. So the first idea in actually trying to detect neutrinos was a fairly crazy scheme. They were doing a lot of nuclear weapons testing in Nevada in the 1950s. And so the thought was, okay, we're going to go and detonate a small nuclear bomb. This thing is going to undergo a immense amount of nuclear fission. It's a fission bomb. You'll have the fireball, and then we're going to try and detect the neutrinos from this weapon going off. And to do that, their idea was, we're going to dig a very deep hole in the ground, and there's going to need to be some backfill to prevent the shock wave from, or the pressure blast wave, I should say, from going down the hole. And what's even better is this whole thing needs to be under high vacuum, because if it's not under vacuum, when you have the shock wave passing through the earth into the excavated tunnel, it will then crush, the pressure waves will couple and it will crush whatever you have. So the idea was this thing can't be connected via air or any other media to the ground or anywhere that the shockwave would be going. So we're going to drop this thing down about a kilometer. The drop would be about a kilometer to get a good signal. They shortened it later, but the first estimate was this entire apparatus would be a kilometer deep. They would drop it onto some foam and would then go and dig it out later. And let's go and do the math on this. Let's see if this would actually work. 20 kilotons is about 84 trillion joules. When you convert that to mega electron volts, that's about 5.2 times 10 to the 26 MeV. One fission reaction will release 200 MeV, so that's about 2.5 10 to the 24 fissions are occurring in the weapon. 6 neutrinos are emitted per fission, so 1.6 times 10 to the 25 neutrinos. And then we're just going to make some reasonable assumptions that half of the neutrinos are emitted above the IBD threshold, the inverse beta decay or neutrino capture 1.8 MeV threshold, and that another half of them are emitted in the few seconds of fall time for what they ultimately said would be about 150-meter hole. Let's assume, fortunately, our detectors are fairly cheap. It's water, plastic scintillator or liquid scintillator, and salts of cadmium, boron, etc. So let's say a 1 meter cube detector 100 meters away from the explosion. So that would give you a neutrino flux of about 3 times 10 to the 19 neutrinos per second per meter squared. Then if we want to calculate that as a number of interactions that occur, we have the neutrino flux times the neutrino times the times the number of protons. This number here is the 6.68, the number of protons in 1 cubic meter of water, times neutrino cross section. And drum roll, please, it gives you 15 neutrinos. So that might not sound like a lot, but that actually would have worked. And I will, tell you in a little bit why 15, let's call it a 20 neutrinos can do a lot for fundamental science. Unfortunately, this experiment never happened, as crazy as it sounds. That may be for the best, but they came up with a better idea, which was the Cowan and Reines experiment, which was going to be basically the same concept, but outside of a nuclear reactor instead of a nuclear weapon. And that became a better idea because by the 1950s, gigawatt scale nuclear reactors were being developed, and there wasn't a need for using a nuclear weapon. You had enough neutrinos from that. So the first experiment was Mr. I was the detector, and it was a drum of water filled with cadmium salt, and it was at the graphite moderated reactors in Washington State. And this experiment was actually a bit inconclusive. They found that they had a large muon background, and the muon lifetime is about 2.2 microseconds. So that's about the same time scale of a neutron capturing. So they had a hard time differentiating neutrons from neutrino capture versus muons decaying and producing a neutron via spallation or some other source inside of their detector. So they upgraded their experiment, and they made a couple of design changes. They made a sandwich. This is not to scale, but you would have the scintillator. They used liquid scintillator between or sandwiching your water and cadmium target. So the neutrino would come in to the neutrino would come into the uh, target here, produce the positron, which would then produce these 511 uh, back-to-back gamma rays. And then the neutron would go and capture on the cadmium. And when cadmium captures neutron, you get a lot of gamma rays. So what they would do is they would say, okay, we have this sandwich. We want to detect a event in both in two layers, one above and one below the water and cadmium target. And what you would then look for in your, where you would look for in two, so this is their three detector channels here. And they would look for some low energy signals, which would then be followed by these much higher energy signals with a delay of about, 2 to 5 microseconds. They set their entire coincidence window to 10 microseconds, but that was just for the initial analysis, and then tightened it up a little bit later. And then between being underground and this sandwich geometry, they were successfully able to measure signals. They did several experiments, like they put it on train tracks, so they were able to move it, a few meters farther and closer from the core and measure, that something is changing. They measured whether the reactor was on, off, etc. And they sent a letter to Wolfgang Pauli in 1956, who said that, after 30 years, we are happy to inform you we have definitively detected neutrinos from fission fragments by inverse beta decay of protons. Wolfgang Pauli's response was, everything good comes to who knows to wait. And Hans Bethe's response was, don't believe everything you read in the papers. Um, Frank Reines was awarded the Nobel Prize in both of their names in 1995. Unfortunately, by that point, Clyde Cowan had passed, and the Nobel Prize is not awarded posthumously, so Frank accepted it on both of their behalfs. So then, if you noticed in a comic that I had earlier, 100 trillion neutrinos pass through your body every second. It's actually a lot more. That's about how many pass through your thumb every second. Through your thumbnail is about 60 neutrinos. And the question is, where are all of those neutrinos coming from? And the sun, this big ball of nuclear energy 93 million miles away, is emitting a tremendous amount of neutrinos. But this does not have a hat over it. It's not an anti-neutrino. So the next question that people had was, okay, we want to demonstrate that nuclear reactions are going on inside the sun. And we said, okay, we have nuclear weapons, we have nuclear reactors, we've measured neutrinos from, or the anti-neutrinos from nuclear reactors, but can we detect the neutrinos from the sun itself? And this is actually it's really difficult without neutrinos to prove that nuclear fusion is occurring within the core of the sun. And the reason for this is, while light might take only about 8 minutes to reach the Earth, the mean free path of a photon, so it's the distance a photon travels before scattering inside the core of the sun, is much less than a millimeter. So it actually takes light about 200,000 years to reach the Earth. So any energy in the form of photons that that's produced in the core of the sun takes nearly 250,000 years to propagate to the surface of the sun before it's emitted. And in that long time, it also thermalizes, so everything bounces around and obscures the signature of nuclear fusion. Neutrinos, on the other hand, don't bounce at all, hardly interact, and so they actually only take about 3 seconds to leave the sun, traveling near the speed of light, plus then the 8 uninterrupted minutes to reach the Earth. So the idea was, okay, let's see if we can detect the neutrinos from the center of the sun, and therefore prove that uh, neutrinos are being emitted from the sun, and therefore also prove that nuclear fusion is the power source of the sun. So this is the beginning of the solar neutrino problem. So while Hans Bethe initially came up with the ideas for what powered the sun, a lot of the math and specific calculations fell on not a student of his, but a younger colleague of his, John Bacall, who came up with three main the three main fusion cycles that are occurring. There's what's called the PP chain, which is proton-proton fusion, and you get various reactions there. The strongest signals actually being you produce boron 8, which then decays to beryllium 8, which then emits a positron and an electron neutrino. You also have what's known as the CNO cycle, where carbon switches between oxygen and nitrogen. And in this, you also have neutrino emission. And then the last is the helium proton, that helium 3 plus a proton goes to helium 4 plus a positron plus a neutrino. So all of these neutrinos are occurring in the sun. And it's relatively easy to calculate what the energy of these neutrinos are going to be, because these are relatively simple nuclear reactions, or actually fusion reactions are more simple than fission reactions from a math standpoint. They're, 2 or 3 bodies on each side of the equation, as opposed to these radioactive fast fission fallouts. So you can use fusion you can use the fusion to estimate, okay, what are the relative shapes and relative intensities of the neutrinos. But what you can't do is measure the absolute quantity of neutrinos just from the fusion reactions alone. And John Bacall did a lot of math, and it turns out the flux of neutrinos is related to the temperature of the core to a very, very high exponential power. So it turns out that for the boron 8 neutrino, which is this, let's see where, this structure here. So it's the highest energy neutrino, and also when you integrate, it's the highest total flux neutrino, with the exception of the PP neutrinos from the proton-proton chain. And that relies on the number of boron 8 neutrinos that you get turns out to be related to the core temperature of the sun to the 25th power. And if you propagate a 1% error in your temperature calculation, you get a 30% error in your neutrino flux. And when you count for all of the different neutrino cycles, a 1% error in core temperature can amount to at least a 300% deviation. So now I'll re-show this picture of John Bacall, and he's this young theorist, and these are the deer in the headlight eyes of what have I gotten myself into. It's really brutal math. So that's our neutrino source. We're kind of going the opposite of detection of antineutrinos, but how do we detect these neutrinos which aren't antineutrinos? And you likely have talked in previous lectures in the course that you have electron capture decay, which is a nucleus captures an electron, which then goes to another nucleus and emits an X-ray, but it also emits a neutrino. So the same logic applies to uh, inverse beta decay or neutrino capture, that you can have something like chlorine 37, which is a stable element, capture a neutrino and go to its parent, argon 37, which is radioactive, and then remeasure the decay of argon because as I mentioned, it's radioactive. And so it will redecay with a 35-day half-life, and you measure that small energy signal from the amount of produced argon. So there's three gentlemen in the picture. There's, going from right to left, there's Ray Davis, who came up with this idea for a chlorine detector, John Bacall smoking the corncob pipe in the middle, and Koshiba, who we'll talk about in a little bit, but also relevant to solar neutrino detection. And so the thought was, we will put this experiment deep underground where it can be shielded from everything with the exception of the solar neutrinos. And so they dug out 100,000, or the volume for a 100,000 gallon tank of dry cleaning solution, which is this carbon 2 chlorine 4, and came up with this really complicated pump like system to extract argon produced inside the chlorine tank and measure it with Geiger counters. And this is a picture of John Bacall swimming in, or not John Bacall, that's Ray Davis swimming in the tank when they filled it with water. And the solar neutrino experiment of chlorine was probably one of the most successful experiments of all time. It ran for nearly 25 years. There's a break in the middle, and this is the average neutrino on the right scale side. There's the average neutrino argon production. So you got an average of about 2.5 argon 37 atoms produced per day, and that corresponded to an equivalent of about half a decay of argon detected per day. And what's actually very fascinating about this plot is when you fit trends to it, and plot these trends, it actually matches very closely with solar output. So we can measure how much energy the sun is producing, and they correlated this to they correlated this to the solar activity to the neutrino rate observed in the chlorine detector. So how does this correspond? Well, they measured 2.5 neutrinos produced a day, or half an argon decay per day, but the expectation was about 8 neutrinos would be produced per day. So that's a fairly big difference. They didn't know if it was the experiment or the theoretical calculations. So there was a different series of experiments, which is basically the same exact concept as the chlorine, except instead of chlorine 37, it's gallium, which then gallium 71 captures a neutrino, goes to germanium 71, which then decays and is measured. And similarly, the gallium measurements only measured about half the expected neutrino rate. So then everyone thought, okay, maybe it's something to do with electron capture decay, and we don't understand anything there. But the third gentleman in this picture, Koshiba, came up with an idea of detecting solar neutrinos via Cherenkov light. And I believe Cherenkov detectors were discussed earlier in this course, but a brief overview is nothing can go faster than light in a vacuum, but when a charged particle goes faster than light in a medium, it creates a sonic boom-like thing. So the idea would be these MEV neutrinos would hit electrons in their target detector and would produce these light cones called Cherenkov cones, which they could then detect. And this is a very famous picture on the right, which is two men in a little inflatable boat in the Super Kamikoda detector, which was this enormous underground, again, this was several miles underground, or about a mile and a half underground, enormous volume of water. And this is on the left is the kind of image that they can produce of these Cherenkov cones, so they're in a boat, and then beneath them in the water is all the photomultiplier tubes and all the photomultiplier tubes on the wall. And actually, when this was running in 2001, there was a massive, massive failure of Super Kamikoda, where the PMTs started imploding, and it caused a chain reaction. And apparently, according to the people in the control room, they thought it was an earthquake and that they were all about to die from the immense sound of all these vacuum tubes breaking and the water pouring in. Fortunately, everyone was fine, but that was the end of that iteration of the experiment, but they got it back up and running with upgrades. So, but the nice thing about Cherenkov detectors is that you can kind of take an image and project back the cone. So they were able to even take a picture of the sun in neutrino. So there's the picture of what the sun looks like with the visible eye, and what the sun looks like in Super Kamikoda's picture of the neutrino, or picture of the sun in neutrinos. Unfortunately, Super Kamikodo also found that they measured only about half the number of neutrinos expected. And so the thresholds for each of these reactions is different. So at this point, they're like, okay, the theory has to be wrong. But John Bacall and company were adamant that they had their calculations correct and knew what was going on. And what ultimately ended up breaking the tie of whether this was a theory or an experimental uncertainty was the Sudbury neutrino experiment, the SNO experiment, which was, okay, rather than water or a proton related target or an electron related target, we would have heavy water, deuterium based target. And there's two reactions of neutrinos on deuterium. You can either have a neutrino, breaking this deuterium apart into two protons and an electron, or any kind of neutrino can break this deuterium apart, in which case the neutrino is preserved, but the deuterium is broken up and you detect the proton and the neutron. And what the SNO experiment found was that there is something called neutrino oscillations. And it was thought originally that the neutrinos were massless particles that traveled at the speed of light. But it turns out that they have a little bit of mass, which the physics of what's going on is a little complicated, but in effect, the neutrino mass eigenstates propagate at different velocities, which means that one neutrino can turn into another. And so there's because of the rate at which they turn into different neutrinos is related to the relative mass, and this could then be calculated for the survival probability. And when you recalculate the neutrino spectrum, expected with the neutrino oscillation losses, because the chlorine, gadolinium, and water Cherenkov detectors cannot see muon or tau neutrinos. They got a perfect match. Ray Davis and Koshiba won the Nobel Prize for their detection of solar neutrinos in 2002. And Art McDonald and Kichida, I'm mispronouncing that, I know, won the Nobel Prize in 2015 for the SNO experiment, and Takaki did a similar experiment in an upgraded version of Super Kamikodo. And as we're running behind, we're not talking about that. But I spent a day with Art McDonald once a few years ago, and he's one of the nicest people I've ever met. John Bacall, unfortunately, did not win the Nobel Prize, and you can either say that this is, the Nobel Prize in Physics has a long-running um, bias against astrophysics. Edwin Hubble, for example, did not win it, but his contributions to science were immense. He was one of the founding fathers of the Hubble Space Telescope, in addition to his work in solar neutrino problem. So try to go through the rest relatively quickly. We're short on time. Since the solution to the solar neutrino problem, the Borexino neutrino experiment kind of combined multiple ideas. They included both scintillators and water Cherenkov detectors. And the idea was they would be able to detect a solar neutrino and see the Cherenkov light, but then also see the scintillation light. And from there, they measure an energy spectrum and can measure not just the number of neutrinos, but the energy of the neutrinos coming from the sun. Then in 1987A, this is going to be why 1520 neutrinos is very important. In 1987, supernova 1987A exploded about 180,000 light years from us in the Large Magellan Cloud. That's the first supernova close to Earth since the Kepler I think this is the Kepler supernova in 1604. And we were able to detect 25 neutrinos from this supernova 170,000 light years away. Unfortunately for Ray Davis, the homestake experiment, the chlorine experiment, was actually down for planned upgrades. So you see there's a little gap in their data rate. They went down for upgrades and repairs in 1986, and we're still down in 1987. But there were 3 experiments running, and one of the Kamikotos, the Irvine, Michigan Brookhaven experiment, and an experiment in the Soviet Union. And between the 3 of those, a total of 25 neutrinos were detected. From this, they measured the neutrino luminosity of supernova, and it's actually 99+% of the energy of a supernova is emitted in its neutrinos. Some other experiments going on today are the Prospect experiment, which is an anti-neutrino detector at Oak Ridge. And I think they're one of the coolest experiments in that they've measured this oscillation within the volume of their detector, and they can move their detector also. So you see there's a 1/r² loss, which is at getting farther from the reactor core, but there's this wiggling going up and down, and that's actually the neutrino oscillation signal. And then there's far baseline experiments, which aim to measure the neutrino oscillations, hundreds of meters to kilometers from reactors. And the idea is they want to measure neutrinos changing into other neutrinos. And then there are accelerator-based experiments where you create muons, for example. The decay of the muons produce muon neutrinos, and then those muon neutrinos are detected hundreds of kilometers away. And this is all to study the question of why neutrinos have mass, and are there additional flavors and other physics goals. Well, this then shows, as the neutrinos travel through the Earth, the probability oscillates. There's also the spallation neutron source at Oak Ridge National Lab, which spallation is using a particle beam to effectively blow up neutrons or nuclei, which produces a lot of neutrons, but also a lot of neutrinos. And it produces a very pulsed neutrino source. And this is a neutrino process actually also very important in supernova physics, which is instead of the neutrino being captured or blowing apart a nucleus, it elastically scatters off of the nucleus. And this was also proposed 44 years ago, in the same solar neutrinos supernova 1987A timescale. And like Hans Bethe was thought to never be found, but was recently measured in 2017. And then that brings us to dark matter, which we have a few minutes left, which is basically how these coherent neutrinos are measured is by these very low energy nuclear recoils. So the thought is if we have this gas of dark matter in the galaxy, which I'm running out of time, so I'll go through fast, but the evidence for that is galactic rotation seems to be about too fast to be accounted for with all the visible light. We expect there to be this WIMP wind that we are then sailing through. And the WIMPs are the dark matter. We sail through it as the sun orbits around the galactic center and as we orbit around the sun. And the idea is to detect these low energy nuclear recoils as we travel through this galactic dark matter wind. And the two experiments, they're two broadly kinds of experiments aimed at measuring this, but they're very similar. The first idea is liquid xenon time projection chambers, which is similar to, you put a large body of a liquid, it's a cryogenic liquid underground, you measure the scintillation from a particle like dark matter hitting one of the target nuclei. And because this is both a scintillator and an electrode, you get a second burst when these electrons hit this electrode. And by the ratio of the two, by the ratio of the ionization signal to the scintillation signal, you can measure if it's a gamma ray or a nuclear recoil interaction. And then the other idea, and this is what I'm working on in Zurich, is low temperature bolometers, which you measure the tiny micro heat produced from nuclear recoils within crystal targets. And we're going to skip through this, but just the targets we're deploying for the Tesseract dark matter experiment. Conclusion, I know I kind of rushed through that at the end, but there's a lot of advanced detector technologies. Dark matter and neutrino physics is highly tied to nuclear engineering, radiation detection and measurement, in that a lot of the processes of measuring neutrons, nuclear recoils, gamma rays are very similar. So I hope that you kind of see how some of the things discussed previously in the course can be used in other ways for astrophysical purposes. And there's lots of experiments going on these days in dark matter as well as neutrinos going forward. So I think then there's a few minutes for questions.
All right, so we have a couple questions in the chat right now.
And if I
So
skipped your favorite neutrino experiment or dark matter experiment, I'm sorry. There's a lot of them over the years.
okay, so someone asked, do we know what accounts for the non-symmetry of mass and charge of different types of fundamental particles, or is that accounted for by antimatter? If so, what makes it anti?
That is not accounted for in antimatter. So the if we go way back to the beginning, the mass of the quarks, sorry. Okay, so these mass, the up and down quark are all about an MeV. The higher quarks go up to a few hundred GeV, and that's relatively well understood. And the mass of the Higgs boson is also relatively understood, as well as the mass of the electron being lighter at about half an MeV. But the mass range of these particles are about we'll say 1 MeV to 100 GeV, and that's known. What is not well known is why neutrinos are so much lighter. And we know the relative mass scales of them, but we also know that their mass scale is, their mass is greater than 0, but less than about 1 eV for the electron neutrino, for example. And we don't know why the neutrinos are so much lighter and how there's a mechanism to generate such a difference in mass scales from the other particles. So this is not well understood, and it's hoped that measurement of these neutrino oscillations, as well as some other neutrino experiments going on, can help figure out what mechanism neutrinos have such a different mass than other particles. But this is a ongoing question in fundamental physics.
Okay, and then do you have time for one more question,
Yeah,
Alex?
yeah, I
Can
think
I
we can
ask
do
you
one
one
or
more?
two more.
Okay, so this one says comment on modified Newtonian dynamics theory that is competing with dark matter theory.
Um, so modified Newtonian dynamics, so we go back down to this. So I went through this quickly, but the idea is we have this observational evidence from stars that, we can measure the speed of the galaxy rotating on its axis. And then from the interstellar gas, we can measure much farther out. And if we account for all the mass and all in the form of stars, interstellar dust, gas, etc., we expect the velocity curve to look, like this. And there's a big difference between these two. The one idea is that there is dark matter. Another idea is that the Newtonian assumption, which is the assumption of general relativity that goes to Newtonian physics on a long time scale or long distance scale, might be incorrect, and that there's a different solution to a modified Newtonian solution to the general relativity field equations. The hardest challenge that modified Newtonian dynamics has to overcome, in my opinion, is they need to come up with an experiment that only modified Newtonian dynamics can predict, while simultaneously, this is another field of physics, but recently the merger of super heavy black holes, two black holes spinning into each other and colliding, was measured, and you get a really good test of general relativity, and as well as across different field strengths, including part of the Newtonian limit from these black hole merger events. And so the big challenge I see MOND facing is you have to come up with a theory that also explains this galactic observation, but doesn't break what we've observed from black hole mergers. And the black hole mergers have killed a lot of MOND theories. Not all, but that's a uh, challenging line to go through. All right, I think
All
one more.
right. Yeah, so this one says if muons decay, how can they be fundamental particles?
That is because fundamental particles can decay into other fundamental particles. So going back up, let's go to a clean one here. So these particles can decay that way. Well, neutrinos are stable, but the muon, for example, decays into the electron and a muon neutrino. So they can decay, fundamental particles can decay into other fundamental particles. And the question there is the proton stable? So which is a, question of, are these guys stable? Or can they go into, something even lighter that we wouldn't know? That's actually what the Irvine, Michigan Brookhaven experiment was looking for. They were looking for uh, water decaying, the proton in the hydrogen atom in water decaying. So if the proton does decay, then yes, these would not be the most fundamental particles. but the electron is a bit more fundamental than the muon and the tau because the muon, they decay that way. But we have not seen any evidence of anything else that they can decay into. No proton decay experiment or electron decay experiment has ever seen anything similar to dark matter. Doesn't mean it's not there, and that's when I kind of drew the cartoon graph of the fundamental particles in time. That's why we don't really know where in this space we're going. All right.
All right. Thank you so much, Alex. And thank you everyone for coming to this talk.